Hello, this is Mrs. T from Mrs. T's Chem Talk, and this is going to be a video of the Chemistry Regents January 2017, and I'll be going over questions 1 to 30 in this video. In case you don't know who I am, my name is Beth Chiminello. I'm a chemistry teacher at Calhoun High School in Merrick, New York. So to start off, for the January 2017 Regents, looking at question number 1, in class we called it the Violet exam, and it says, which statement describes the location of two types of subatomic particles in the helium atom? And remember that when we talked about the atom, we said that in the nucleus, we have the protons and the neutrons. Remember that the protons are positive, the neutrons are neutral, so that makes the nucleus have an overall positive charge. We said that the electrons were outside the nucleus in orbitals. For question number 2, an atom contains 6 protons, 6 neutrons, and 6 electrons, has a mass of approximately what? So if we want to get our mass number, is equal to the number of protons plus the number of neutrons. So we're going to add the 6 protons plus the 6 neutrons, and we're going to get a mass of 12 atomic mass units approximately. Remember also that that's also going, since that's our mass number, that means that the mass number would be 12. That means that the number of protons tells us the atomic number. The atomic number would be 6. And remember, if we look at the periodic table, an element with an atomic number of 6 is carbon. So we're going to put the carbon symbol here, and this would be an isotope of carbon. We can also do the mass number minus the atomic number to get the neutrons. Remember, MAN, mass number minus atomic number, gives us neutrons. For number 3, it says, which term identifies the most probable location of an electron in the wave mechanical model of the atom? Remember we said that they can also call this wave mechanical model the modern model. And this modern model of the atom says that electrons are in orbitals outside the nucleus. We said that electrons are not moving in fixed paths. Which means that this part of the Bohr model was wrong. So electrons are not in these fixed paths called orbits, but rather electrons are found in these orbitals, which are the areas of most probable location. Question number 4 asked, which element in the ground state has an atom with the greatest number of valence electrons? So we're going to have to look up tin, sulfur, arsenic, and fluorine on the periodic table. If you don't know the symbols, you can look up the symbols on table S. When you look at table S, tin is SN, sulfur is S, arsenic is AS, and fluorine is F. So in case you didn't remember those, but we're going to look up SN, S, AS, and F, and we're going to try to look up for the valence electrons. And the valence electrons are the last number in the electron configuration. So we're going to look and see which one has the highest last number in the electron configuration. So let's switch over to the periodic table, and we're going to look up SN, which is a metal. So we're going to find SN. We're going to find sulfur. We're going to find arsenic, which on table S, you can also find the atomic number, which would make it easier for us to find these things. So we're looking for the last number in the electron configuration for these 4 elements. And when we look at the last number in the configuration, tin's last number is 4, arsenic's last number is 5, sulfur's last number is 6, and fluorine's last number is 7. So that means that fluorine has 7 valence electrons, which was the highest number. So we're going to go back to the question and we're going to say, okay, fluorine is the one that had the most valence electrons. Number 5 says which group on the periodic table has 2 elements that exist as a gas at STP. So we can actually use both table S and the periodic table, and we need to look at group 1, 2, 16, and 17. So I'm just making this note so that when we switch over we can see it. So we're looking at group 1, 2, 16, and 17. So for group 1, we should know that hydrogen is a gas. I'm actually going to circle all the elements that exist as a gas at STP, and I'm going to do that with the highlighter so that we can see it. So we have hydrogen, all of group 18. We have nitrogen, oxygen, fluorine, and chlorine. These are the elements that exist as a gas at standard temperature and pressure. And we want to know of group 1, group 2, 16, and 17, which one had 2 elements that exist as a gas at STP, so that's going to be group 17. Just as a side note, we also have 2 elements that exist as liquid on the periodic table at STP, and that would be mercury and bromine. So those are my liquids, and here are my gases, just so you can remember those. All of group 18, remember group 18 is called the noble gases, and then NOFCl. So the green ones that I highlighted, hydrogen, helium, NOFCl, and all of group 18 are the gases. Bromine and mercury are liquids at STP. The rest of the table, every other element is going to be a solid at standard temperature and pressure. So we want to know which list contains a metal, a metalloid, and a nonmetal. So we're going to go back to the periodic table again. So everybody, all of the elements here, including aluminum, including tin, including bismuth and polonium, and here we're not going to really worry about. And at the bottom here, all these elements at the bottom, those are all metals. If we want to look at the nonmetals, remember hydrogen is a nonmetal, and then all these elements over here, including helium. I don't know why this isn't working right, are nonmetals. The elements that touch the zigzag line in 2 places except for aluminum and polonium, these are going to be my metalloids. Okay, so those are going to be my metalloids. Remember, that can also be called semi-metal, and semi-metals have properties of both metals and nonmetals because they're on that borderline there. What is the charge of the nucleus on the nucleus of a copper atom? So we need to look up copper on the periodic table, and copper has 29 protons in its nucleus. 29 protons in the nucleus means, so I have my nucleus with 29 protons and some, we have 29 protons and some number of neutrons. Now, protons are positive, neutrons have no charge, which means that we have 29 positive charges in the nucleus and then a bunch of neutral charges in the nucleus. So anytime they want to know the charge of the nucleus, this is also called nuclear charge, and this is equal to the number of protons with a positive sign. For number 8, we have elements that have, different forms of the same element that have different properties. These were called, not alu, sorry about that. These were called allotropes, and remember that diamond and graphite are also called allotropes, considered allotropes of carbon, and allotropes always have different structure and different properties. Their different structures give them different properties. Number 9 is a definition question. It's asking about a compound, and remember, a compound is a substance. The other kind of substance would be elements. Elements and compounds are the only things that are considered substances. And compounds have to be chemically combined. We also know that compounds are in a fixed proportion. That means that the ratio and the percentages stay the same. If we change the ratio or we change the percentage, we change the kind of a compound that we have. Now we also have, to contrast, things called mixtures. Mixtures are physically combined, and mixtures have a variable proportion. For number 10, we're actually going to look at table S. So we're going to have to look up Mg, Na, Rb, and Sr on table S. So I'm just going to find table S. Unfortunately, I'm sideways here, but the boiling point is on table S here. Make it a little bit bigger. And for magnesium, we have a boiling point of 1363. For sodium, we have a boiling point of 1156. For rubidium, which I think is on the note, here we go. For rubidium, we have a boiling point of 961. And for strontium, we have a boiling point of 1655. So we're looking all of this information up on table S. On table S, we have atomic number, symbol, name, first ionization energy, electronegativity, melting point, boiling point, density, and atomic radius. All of this information is found on this table. So when we go back, they were asking for the highest boiling point, and of the 4 numbers that I wrote down, strontium was the highest number, so that's why it was the highest boiling point. How many pairs of electrons are shared between the nitrogen atoms in a molecule of N2? If we look at nitrogen on the periodic table, we see that nitrogen has 5 valence electrons. Its electron configuration is 2-5. So if nitrogen's electron configuration is 2-5, that means it has 5 valence electrons. That means that if 8 is the stable number and it has 5, so we have our happy minus have, that means it has to bond 3 electrons. If each nitrogen atom has to bond 3 and keep 2, so right, these are the ones in the bond, these are the ones that are being kept, we have a triple bond in the molecule of nitrogen. Remember that every pair of electrons that's shared can be rewritten as a line between. And now, if I cover up one of the atoms, I get 2, 4, 6, 8, 2, 4, 6, 8. Each atom now, by sharing, has a stable octet. This is also a covalent bond because it's 2 atoms of nonmetals, and it is a non-polar covalent bond because the electrons will be shared equally because it's atoms of 2 of the same nonmetal. They have equal electronegativity, so they have the same pull on the electrons, so they will share those electrons equally. For number 12, on the other hand, we're talking about the molecule, and for molecules, symmetrical is nonpolar, asymmetrical is polar. So a molecule is nonpolar if it has a symmetrical distribution of charge, molecule, symmetrical, nonpolar, asymmetrical, polar. Remember, so these are the ones with no charged ends. Asymmetrical polars are the ones with a positive side and a negative side. For number 13, if we said that 2 atoms with the same electronegativity have a nonpolar bond, the more difference there is between the electronegativity, the more polar the bond. So bond polarity is how unequal are the electrons shared. The more difference there is in electronegativity when you subtract, the more polar the bond is. The less difference there is between the 2 electronegativities, the less polar the bond is. Remember, we said that there are 5 factors that affect the rate of reaction, and those 5 factors are temperature, concentration, remember that's only for solutions, surface area, nature, and presence or absence of a catalyst. Temperature, concentration, and surface area, if we increase the number of effective collisions. Increasing the number of effective collisions makes the reaction go faster because remember, according to collision theory, reacting particles must collide or hit each other. They must have enough energy to meet the activation energy, and they must collide or hit in proper orientation. If we can make the collisions more effective by increasing the temperature, the concentration, or the surface area, we can speed up the reaction. Remember that the nature of the reaction, the nature of the reactant says that some particles react more quickly or more slowly just based on how they are made up, and that ionics in solution are just naturally fast. Organic compounds are naturally slow based on their necessity for a high activation energy. A catalyst, however, speeds up a reaction by lowering the activation energy, and it does this by creating an alternate reaction pathway. We also call this a mechanism, and it's basically the series of steps that are taken for the reaction to happen. A reaction that uses a catalyst will go faster because of the lower activation energy. More of the collisions will be effective. Remember also, for a catalyst, does not shift the equilibrium because it speeds up both reactions equally. So there is no effect on the equilibrium. It does speed up both reactions, but because it speeds them up equally, they're still going at the same rate. For number 15, substances that can be decomposed by chemical means are going to be compounds. If you're looking for compounds, you want something that's not an element. Elements are found on the periodic table and on table S. So if you're not sure which of these are elements versus compounds, you can look on the periodic table and look for krypton and methane and the cobalt and the zirconium. But if you're not sure what those names are, you can look at table S actually, because you can look for cobalt, krypton, methane, zirconium on here, and here's chromium, here's cobalt, and here is zirconium. So those three are elements. If those three are elements by process of elimination, methane is going to be your compound. Compounds can be decomposed by chemical means. Elements cannot be decomposed by chemical means. For number 16, remember that mixtures would be two or more substances physically combined, which that means that they can also be separated physically. So if they're physically combined, we're looking for, remember, aqueous means that it looks like this, that it's AQ, means that it is dissolved or mixed with water. Okay, it's mixed with water and it dissolves to make a homogeneous mixture. But something like a solid, a liquid, or a gas, we only use those symbols or those terms when we're talking about a pure substance, and pure substances by definition are not mixtures. Some other examples of mixtures that they love to ask about or mention on the Regents exam: air is a mixture, soil is a mixture, and salt water is also a mixture. Remember that mixtures have a variable proportion. You can have more dissolved or less dissolved, or the components, their percentages can change, and it could still be considered a mixture. For compounds, which are substances, the proportion must be fixed. It has to have the same percentage every time. For number 17, another mixture question. When we separate mixtures, we have to separate them by physical means. And for sand and seawater, we're going to separate this by filtration. which always separates by particle size. Remember that for filtration, filtration is going to separate a solid from a liquid. The solid will stay behind in the filter paper. The liquid plus whatever is dissolved will go through the filter paper. So the solid will stay behind, and the liquid and whatever is dissolved in it will go through the filter paper. For a chemical change, you must change which substance you have. Evaporating, subliming, and melting are all phase changes. Phase changes are always physical. Evaporating is going to take the liquid and put it to gas. Remember, this is different from vaporization. Vaporization is boiling, which has to happen at the boiling point, which means that the vapor pressure has to equal atmospheric pressure. Evaporating happens at all temperatures in an open container. As the molecules move away from the surface of the liquid, they evaporate into vapor. Subliming, remember, is solid directly to gas without going through the liquid first. Things that sublime usually have weak intermolecular forces of attraction. Melting, remember, is solid to liquid, and solid to liquid, again, is a phase change. Liquid to gas, and solid to liquid are all on the heating curve and are all endothermic phase changes, which means they absorb energy. Rusting, on the other hand, is actually making a whole new substance. Rusting of iron is going to be iron combining with oxygen in the air to make an iron and oxygen compound. For number 19, which term represents intermolecular force in a sample of water? The type of intermolecular forces of attraction that we talked about dispersion forces, which, remember, dispersion forces happen in all types of molecular substances, and they're weak forces based on just the random movement of the electrons in the sample. We had dipole forces, which for an individual sample would be stronger than dispersion forces, and dipole forces are based on the positive side of one molecule attracting the negative side of another molecule. So this is only something that's present in asymmetrical polar substances. And then we also had hydrogen bonding, which is not a covalent bond. Just because the name says bonding in it, it's actually an intermolecular force of attraction. Hydrogen bonding happens between molecules of water. So it would be one molecule of water attracting another molecule of water. This is not a hydrogen bond. It also happens in ammonia and HF. So it's any time hydrogen is bonded to F, O, or N, the intermolecular force of attraction can be hydrogen bonding. Covalent bonding is a regular bond type. Metallic bonding is a regular bond type in metals. Ionic bonding is a metal plus a nonmetal Covalent bonding is nonmetal plus nonmetal. So covalent bonding has sharing electrons. Metallic bonding has free moving electrons. Ionic bonding has a transfer of electrons. Hydrogen bonding is an intermolecular force. For number 20, the key word here is crystalline. They sometimes also say regular, geometric, to mean the same thing. And this is your key word that we're talking about, a solid. Remember that gas is random arrangement, very far apart. Liquid is sort of random arrangement, but close together. Slightly further apart than the solid, but not as far apart as the gas when we're talking about the liquid. And aqueous is a mixture where we have dissolved in water. Number 21, which term is defined as a measure of randomness of the system? This is a definition question. I always remember that the R in entropy means randomness, so entropy is the randomness. The other word that kind of sounds like this is enthalpy, and I say that the H means heat. So entropy, the R tells us that it is randomness. Enthalpy, or enthalpy, the H tells us heat. Now remember, for randomness, solid has the least entropy. Gas has the most entropy, and liquid is in between. Which formula represents an alkane? We're going to look at the reference tables, and we're going to look at table Q. So when we look at table Q, it says that alkanes have the general formula CnH2n plus 2. So what that means, CnH2n plus 2, that means that the number of carbons has to be doubled, and then you add 2 to get the number of hydrogens. So this is equal to the number of hydrogens, so it can't be that one. This one is only double, and this one is only add 1. So 3 times 2 equals 6. 6 plus 2 equals 8. So C3H8 fits this general formula. A chemical reaction is different from a physical reaction. Deposition, remember, is solid to gas. I'm sorry, it's not. Deposition, remember, is gas to solid. Sublimation is solid to gas. Vaporization is liquid to gas. Those three are all phase changes. And phase changes are all physical. Combustion is burning. It is also combining. With oxygen. And we said that in our organic chemistry chapter, that if we took a hydrocarbon or other organic compound and combined it with oxygen, the two products would be CO2 and H2O. Now this isn't balanced, okay? But if we balance it, we could put a 2 here to get the carbons both to 2. We could put a 3 here to get the hydrogens both to 6. That makes 4 oxygens, and 3, that makes 7. So we said we'd go in and put a 3.5. And then when we have a half like that, because 3.5 times 2 is 7. When we have that, we're going to go through and we're going to double all of the coefficients to get the right ones. This reaction goes from ethane, which is C2H6, plus oxygen, which is O2, to carbon dioxide and water. We've changed what substances we have, and by changing what substances we have, that makes it a chemical reaction. The list of organic reactions included esterification and polymerization. Remember, esterification is acid or organic acid plus alcohol yields ester plus water. Remember, we said we have Kuchian ester because the ester has a COOC functional group. Remember that polymerization was the one where we have some number of a compound or some number of small pieces, which would be called monomers, and we make them become connected. Remember, when we have a coefficient, it means that we have them separate. A subscript means that they are bonded chemically. And if we take many, many monomers and join them, we make a polymer. And we said that was another type of organic reaction. For number 25, in a redox reaction, the total number of electrons lost is always equal to the number of electrons gained. Remember that we balance half reactions to make sure that they have the same number of electrons in each, and this is because of the law of conservation. The law of conservation says that mass, energy, and charge are always conserved in any chemical reaction. When we talked about oxidation, this was part of redox, which is oxidation reduction. We said that oxidation and reduction always happen at the same time. We said that gaining electrons is reduction and the charge goes down. Losing electrons is oxidation and the charge goes up. We also said that for a reduction half reaction, the electrons go before the arrow. We said that for losing electrons oxidation, the electrons go after the arrow. We can use the word redox, reduction electrons first, oxidation electrons last. (27) The electrical conductivity in an aqueous solution. We said that solutions conduct when they have mobile ions. The solutions that conduct would be acids, which we can find examples on table K, bases, which we can find on table L, and ionic compounds, which is usually a metal plus a nonmetal, or something from table E plus a metal or a nonmetal, or something positive from table E with something negative from table E. But these substances, when we dissolve them in water, will separate into ions, and those ions will be able to move, which is why solutions can conduct. That was the one with the light bulb test, where if a solution was an acid solution, a base solution, or an ionic compound solution that was soluble, we would have the light bulb be able to light because the electricity could conduct through the solution. This is different from metals because metals conduct because of mobile electrons. So this is different. Metals and solutions conduct for different reasons. For number 28, an electrolytic cell versus a voltaic cell. We know that an electrolytic cell requires a battery, but a voltaic cell is a battery. An electrolytic cell is non-spontaneous, but a voltaic cell is spontaneous. We know that an electrolytic cell takes electrical energy and converts it to chemical, and a voltaic cell takes chemical energy and converts it to electrical. The electrolytic cell always requires the outside energy source for the non-spontaneous chemical reaction to occur. And our electrolytic cell will always have that picture of a battery, or it will be shown to be plugged into the wall like your cell phone charger, something like that. Another, besides just charging a battery, another thing we can do with an electrolytic cell would be electroplating. Remember that electroplating is electrolytic, and that's where we cover the surface of one metallic object with atoms of another metal. For these electrolytic and voltaic cells, things that go for both of them would be an ox and big red cat. Anox means that the anode is always oxidation. Reduction is always at the cathode, and the cathode always gets bigger. Electrons always flow from anode to cathode through the wire. Ions will always flow in the salt bridge or in a solution if it's just one cell, but there has to be a way for ions to get to the anode and the cathode to balance out the charges of the solutions. Electrons always flow through the wire from anode to cathode. Ions always flow through the salt bridge or through the solution. If we want to know which radioisotope emits particles having the greatest mass, we're going to have to look at table N. So we're going to look at cesium-137, Fe or iron 53, Fr or francium 220, H or hydrogen 3. So if we flip back to the reference tables and look at table N, on table N at the top we have the nuclide symbol, the nuclide name, and the decay mode. So I'm going to write down the decay mode for each of these, and these are in alphabetical order based on the symbol. So cesium-137 has a decay mode of B-, Fe53 has a decay mode of B+, Fr220 has a decay mode of alpha, and H3 has a decay mode, I'm just going to circle those so you can see where I'm getting this information from, and H3 has a decay mode of B-. The other place that we can look is table O, because table O has the mass numbers of these particles. So I'm just going to erase these little circles here. And if we look, B-, which is a beta particle, has a mass number of 0 because the beta particle has a mass of 1/1836 of an atomic mass unit. B+, or positron, also has a mass number of 0, which has the same mass as the beta particle, but the alpha particle has a mass number of 4, which means that its atomic mass, or its approximate mass, is 4 atomic mass units. So francium-220, which emits alpha, emits particles with the greatest mass. So that was a table N and table O question. And this is the final question for this video. There will be 2 other videos for the rest of the exam, so be sure to tune into those. It should be the next one in the playlist if you're following it through the playlist. At this point, if you have enjoyed this, you can certainly subscribe to the channel and look for some other Regents chemistry and also AP chemistry videos on that channel, Mrs. T Chem Talk. So which term represents a nuclear reaction? remember that nuclear reactions usually show, so if we have our symbols, they usually show a mass number and an atomic number if they show it out. So maybe it would be like 2 over 1H plus 3 over 1H, or maybe it would say something like FR 220 and then an arrow, but you're always going to see these numbers. And on one side of the arrow, you're going to see one set of symbols, and on the other side of the arrow, you're going to see a different set of symbols, because all nuclear reactions, or usually nuclear reactions, are going to change which element we have, and that's the definition of transmutation. When an atom of one element turns into an atom of a different element. And when this happens, we have transmutation. Now, combustion, fermentation, and saponification were all on the list of organic reactions. Remember, combustion has oxygen as a reactant and CO2 and H2O as products. Fermentation makes alcohol. Saponification takes a base and fat to make soap and glycerin, or some books say glycerol. The transmutation reactions can be natural or artificial. Natural would have just one reactant. Artificial would have two. Also, for any nuclear reaction, they give off way more energy. So they are way more exothermic than regular chemical reactions, because a small amount of mass is converted into energy. And that mass to energy conversion, very, very small amount of mass deficit, will give us a huge amount of energy given off. So again, this has been the Mrs. T's Chem Talk for Regents Chem, for Regents Review. We've been reviewing the Violet exam, which was the January of 2017 Regents. Please tune into the channel for other videos for other Regents Review, AP Chemistry Review, and the rest of this January of 2017 Regents is covered in 2 other videos. Happy studying.